procedure can be put in a form of a flow chart. For this boundary value problem, all that is the you have the governing differential equations, which are discretized first, so it goes through a discretization procedure, and then this yields a system of algebraic equation. Now, it need not be linear. If it is a linear, then directly we can compute if it is a linear boundary value problem. If not, then we have to go for some solution algorithm. I will go for algebraic system. Like Newton's linearization technique and all, and then we get the approximate solution. So this is the basically this is the procedure. So this is the few steps we consider. Now, what are the difficulties or what are the order of approximation? Now, we can have first order, we can have second order central, we can have higher orders and all. Now, which method we'll use and who guarantees that we have the solution, whatever the solution we get, it converts to the solution of the boundary value problem or the differential equations we are looking for. So, now in order to compare the methods, the merits of the methods, we have to know the truncation error. So, we define the truncation error which measures the accuracy of the method is the is the amount by which the exact solution of the differential equation fails to satisfy the approximate, here it is finite difference equation or finite difference equation. Now, the global and local truncation error, because here so far whatever we have done is the finite difference approximation is grid independent. So, global and local truncation error here are the same. So, if it is varies, the way of different approximation or the difference scheme is depending on the grid we are choosing. In that case, the truncation error will vary from grid to grid. So, in that case, we will have a local truncation error and global truncation error different. Now, consistency is a very important thing. So, if the truncation error if the truncation error goes to 0 as the grid size tends to 0, then the finite difference equation or the approximate equation is said to be consistent with the given differential equation. I think given is not an important word, because corresponding to that equation we get the approximate equation. So, if the truncation error goes to 0, if it is some constant value, so this is not consistent. So, consistency is very important. Now, one can show in all the situations whatever we have considered for the boundary value problem, there one can find out the truncation error and consistency. The best way of finding the truncation error is that, see, what we did is, if we call, say, LU equal to 0 is the ODE, and if I call this is FU equal to 0 is the finite difference equation. So, then the truncation error Ti is nothing but FIU, the truncation error. So, normally an order of estimate of the truncation error is important. So, that means we have to write the truncation error at TE in order of H, TE in order of H square for the central difference scheme, and so on. So, normally the truncation error should be expressed as an order of least power of H, as we have mentioned before. So, Ti should tends to 0 as H, the step size tends to 0 for consistency. Now, apart from that, this error, there is another error when we implement this method, numerical method as we described to solve in computer or say calculator and all. So, there will be a round of error will be, because there will be infinite digits and there will be multiplication, divisions and all these things. So, we have to chop out the infinite decimal place to finite decimal and all these things. So, there will be a round of error, that is the most important error while computing. So, then another aspect occurs is the stability. Stability means that if some error is incorporated in the system at certain stage, say either it may be a round of error or misinterpretation of the conditions given. So, in that process, a small amount of error, if it is incorporated. Now, if you see that whether that error grows, if the error grows as we progress in computation, then it is called unstable, and if the error remains same or decays, then it is a stable. Okay. So, stability of the scheme is very important. So, now if the one can say that if the scheme is scheme here, of course, we did not define. So, if the approximation is consistent and stable, then the numerical solution converts to the exact solution. So that much we can say now. Here the stability, particularly for this kind of direct method, whatever we have considered, because here we are not repeating the process, but stability is not a very big issue in the sense that here the number of computations are limited, finite number of computations, finite number of steps are occurring. But if you have a situation where it is with a time integration, so large number of time step has to be followed, so the same process has to be repeated several times. So in that process, if somewhere a round of error is occurring, so that will grow beyond bound. So in that case, it is a unstable situation. Now our next topic we will quickly go through is the solution of partial differential equation. Now when the variable are function of more than one variables, more than one independent variables, so in that case we get a partial derivatives, then partial derivative appears. Say we have come across already the transport equation, the general form of the transport equation governed by an advection diffusion mechanism is of this form. Say this is the C is the one is transported by advection and diffusion. So this is the advective term and this is the diffusive terms. So in 2 dimension, 2D Cartesian, so Q equal to UV, we get del C del T plus U del C del X plus V del C del Y equal to nu del to C del X2 plus del to C del Y2. So we have come across this kind of equation in modeling the many transport phenomena in the previous lectures. Now suppose we consider the simplified situation. So in absence of any advection, that is the mechanism is pure diffusion, we get an equation like this, del C del T equal to nu del to C del X2. We consider only one dimension, 1D transport. So it is only governed by the diffusion mechanism. So say a condition has to be given for this is the time. So what we need to find out t greater than 0 and say Ax is varying between A to B. C0x is something is given, say let us call it Fx, which is called the initial, which is the initial condition. And the two boundary conditions are, say, you C at AT equal to, say, CA, and C at BT equal to CB. So these are the boundary condition. Boundary conditions. So this is the first we talk about how to handle a this is also called the heat flow equation, where C is the temperature and the mechanism is governed by pure diffusion mechanisms, where nu is a constant diffusivity in that case. So how we will solve this? Now here the computational domain, or the domain where we are finding the solution, we need to find out the solution is, say, Tx. T is the time. So this is the line as t equal to 0, and say x is varying from x equal to a, and this is, say, x equal to a, and this line is, say, x equal to b, and this is t equal to 0. So first, as we said before, that we have to construct the grids. So grids we define as say xi Tn, xi equal to a plus I delta x, and Tn equal to n delta t. Now I can vary from 0, 1, 2 up to, say, capital N, and n is varying from 0, 1, 2. This is a semi-infinite. So that means what we are doing is we are taking a step size delta t, and these are the lines over which x is varying. So this is the line over which t is varying. Now what conditions we have given? If I circle, this is the conditions are given. This is the initial condition, and any time this is the boundary condition. Now we adopt a time marching procedure. That is, if we know solution at Tn, time level Tn, then find, use it to get solution at time level Tn plus 1. So that means, so suppose at certain stage I know the solution, this is a Tn plus this is Tn, say, let us call this is Tn. I know the solution at all this level, and this is Tn plus 1. So this need to be obtained. So we denote C xi Tn as Cni. So n is greater than or equal to 0, and I varying from 1 to I can be 0 also, but 0 and n. So let us introduce 0. 0 and n are the boundary conditions. So we need to find out. So C0 I for I equal to 0, 1 to n is the are given, along with, and any time level C n 0 and C n capital N are provided. These are the boundary conditions. Now to get the solution, so what we have presumed that we know the solution at Tn, and we need to find out the solution at Tn plus 1. So this is the level where we need to find out the cross, say unknown 0 noon. So these solutions are somehow obtained. So in other words, say suppose I start with n equal to 0, so that means this is known. Now we need to find out the T1. So if we satisfy the equation at the grid point, say in, use first order forward, difference in T with respect to T and central difference with respect to x. What do you get? This is also called the FTCS. So what I get is Cn plus 1 I minus Cn I by delta t equal to nu by delta x whole square, Cn I plus 1 minus twice Cn I plus Cn I minus 1. So obviously this one can show very easily is a truncation error is first order in time and second order in x. So from here we can write the unknown here directly is the unknown and can be expressed directly in terms of known Cn i's. So that's why I call this scheme is called is referred as explicit scheme. Directly or explicitly, that is the better way. Instead of directly, one can say explicit. So that's why it is explicit scheme. The drawback of this explicit scheme, this scheme is unstable if delta t and delta x does not satisfy this condition. This is the parameter r, delta t by delta x whole square should not, if it is does not satisfy this condition, then it is unstable. So that is another bottleneck, because you have to choose these delta t very small compared to delta x. So now another advantage is another remedy, but one advantage is that we can write directly the Ci n plus 1 in terms of all these Ci n. Basically what we can do is we can write this Ci n plus 1 equal to r Cn I minus 1 plus 1 minus 2r Cn I plus r Cn I plus 1. Now you vary I from 1, 2, etc. n minus 1, you get the all set of values. But it is the drawback, it is unstable and first order in time. So then we go to the implicit scheme. So that means discretize the equation at xi tn plus 1. So what I get is Cn plus 1 I minus Cn I by delta t equal to nu delta x whole square Cn plus 1 I minus 2 Cn plus 1 I minus 1 plus Cn plus 1 I plus 1. This is again order delta t delta x square, but advantage is that it is stable for any choice of delta t and delta x. However, if I vary I equal to 1 to n, we get this will lead to a matrix equation for Cn plus 1 1, Cn plus 1 2, etc. Cn plus 1, this is capital N minus 1. This is n minus 1, 1, 2, n minus 1. So that is another, and this matrix is a which are tridiagonal system. Now again, this is a first order, but the advantage is that it is a stable. So the most popular one among all this scheme is the Crank-Nicolson scheme. So the Crank-Nicolson scheme is, so that is the most popular one. So here what I do is, we have this is t, this is x. So you need to find out the solution. Say this is Tn, this is Tn plus 1. So you need to find out the solution using this Tn. We need to find out the Tn plus 1. So what I do, integrate the equation, the PD with respect to t between Tn to Tn plus 1. So what I get is Cn plus 1 I at grid point xi, at xi, x equal to xi, plus 1 I minus Cn I by delta t equal to nu Tn to Tn plus 1 del to u del to c del x2 dt. Here we have taken x equal to xi. So here we apply trapezoidal rule. Trapezoidal rule. So if we apply trapezoidal rule, this becomes nu by 2 into delta t del to c del x2 at n plus 1 I plus del to c del x2 at n I, because that is the average delta t by 2 in the average values n plus 1 and n. That is the what is referred as the trapezoidal formula. Now we use central difference scheme. Differences. So what I get? If we use central differences, we get Cn plus 1 I minus Cn I by delta t equal to, oh, I'm sorry, this delta t doesn't appear, should not appear here. So there is no delta t. So this is nu by 2. There is no delta t over here. So nu by 2, this delta t now went there. So Cn plus 1 I minus 1 minus 2 Cn plus 1 I plus Cn plus 1 I plus 1 by delta x whole square plus Cn I plus 1 minus 2 Cn I plus Cn I minus 1 by delta x whole square. And this scheme, because this is order delta t square, so this is order delta t square, and here when I have taken the central difference scheme, so this becomes a order delta t square delta x whole square, and also implicit. So now if I this is an implicit and second order accurate. Scheme. So this can be, this scheme can be written as, we can express this scheme as AI Cn plus 1 I minus 1 plus Bi Cn plus 1 I plus Ci Cn plus 1 I plus 1 equal to Ti for I equal to 1 to up to n minus 1, which forms a tridiagonal matrix equation. Matrix A such that A x equal to B, say x is at every time level, this is the unknown C1, Cn plus 1, 2, etc. up to Cn plus 1, n minus 1. So if you solve this, so is a tridiagonal matrix. So every time level for n greater than equal to 0, for each n greater than equal to 0, solve Ax equal to B to get Cn plus 1 I for I equal to 1 to up to n minus 1. So to start the procedure, we start from the initial condition, the given value of whatever the initial conditions is given, and we proceed in that direction. Now, another thing is that, so this Crank-Nicolson scheme is unconditionally stable because it is implicit, stable, and second order accurate both for t and x. So these are the advantages why the Crank-Nicolson scheme is the most popular numerical scheme to solve this heat transport equation. So this question, del u del t equal to del 2 u del x 2, say ux0 equal to, this is the initial condition, sin pi x 0 less than x less than 1, t greater than 0, and u0 t, this is the IC and this is the BC boundary condition, u0 t u1 t equal to 0, this is for t greater than 0 and 0 less than x less than equal to 1. So if I write the Crank-Nicolson scheme, corresponding to this is un plus 1 I minus 1 minus 2 into 1 plus r un plus 1 I plus or minus r un plus 1 I plus 1 equal to r un I minus 1 plus 2 into 1 minus r un I plus r un I plus 1, I equal to 1 2 etc. up to n minus 1, and r equal to, here it is nu is 1, so delta t by delta x whole square. So if I choose delta t equal delta x, if I choose as 1 by 4 and r equal to 1 by 2, let this one. So initial conditions are u0 I equal to sine pi xi, and what you have is un plus 1 0 equal to un plus 1 4 equal to 0. So you get a system always as the A comes out to be minus 1 by 6 0 minus 1 by 6 14 by 6 minus 1 by 6 0 minus 1 by 6 this is the first step, u1 1, u1 2, u1 3, and something like d1, d2, d3. So once we solve this, so we get the u1, u2, u3 at the time level n 1. So with that time level 1 and the boundary condition and initial condition, we go to the next time level and repeat the process till the desired time step we require to find out. So the next one will briefly talk about the solution of higher dimension equations. So that means u can be a function of x, y, and also the convective transport is also taken care. So that will be discussed in the next subsequent lecture. Thank you.